So today we'll be studying about the elastic potential of a system when it is deformed. So first start with what do you mean by potential energy. As you know, kinetic energy is the energy possessed by a system when it is in motion or it has some velocity. When a system has a velocity, it gains potential the kinetic energy, while the potential form of energy is basically due to the is acquired due to its position in a particular force field, or you can say when there is some force acting on a system, then the system, when it is stable in a particular position, that is the system is made to sit stably in a particular point under the action of a force, then that system is said to have a potential because due to that force. Now as you will see that potential energy is the energy of a system due to its position in a force field, while kinetic energy is due to the motion of a system or due to its velocity. So whenever you will see that whenever the position of a body or a system is changed, whenever the position of a body or system is changed while it is acted by a force, the potential energy changes. What I mean to say is that as you will see that at a particular position the system will have some potential energy, but if now we tend to change the position, then the potential energy also changes. So when the position is changed say against the force direction, that is when if work is to be done externally against the force, then the potential is added or it is increased for the system. But if the work is done in the direction of the force, then what will happen? The force, if the work is done externally against the force, potential energy is increased. But if the work done is in the direction of the force, then the force itself does the work, and as the force is doing the work, the potential energy of the system reduces. So you must keep in mind that if we change the position of a system, such that the external work has to be done, and when external work will be done, when work is done against the particular force, then only potential energy will be added to the system, and it is said that potential energy is gained. Otherwise, if the work is done by the force, then system loses potential energy. So for elastic potential, the definition is such: the elastic potential energy of a body in its deformed state is defined as the amount of work done to produce the deformation in the body. So what do you mean by that? Suppose a body is deformed by an applied force. Then as the body is deformed, the force which is called as a restoring force will always try to restore the body to its original configuration. That restoring force, we have to work against that restoring force to keep the body in its deformed form. So hence the elastic potential energy is the work done against that restoring force to keep the body in its deformed form. So now first we will discuss about the elastic potential energy due to longitudinal strain. Now as you can see, for a longitudinal strain, another thing, a small input, say elastic potential energy of the body, that is which is per unit volume volume is actually known as its energy density. It's called its energy density. So if you are asked to find the energy density, what you have to do, you have to find the elastic potential energy and then divide it by volume, you will get energy density. So the first case we will take for longitudinal strain. So for longitudinal strain, so when a longitudinal strain is produced, suppose there is a long bar or a rod of length L. So this is the length, this is the rod of length L. Now if we apply a force such that the rod is deformed and the length is increased, say by delta L, this is the force applied. Now this is the force which is applied to deform the body, but there is a force, say Fr, which this is the restoring force which is trying to pull the rod to its original configuration. So Fr is restoring force, F is applied force. So as we at equilibrium, say when we apply the force F, then the rod will keep on increasing till it reaches, say L plus delta L, which is increased by delta N length, and it will stop. So this is the point of equilibrium. So in equilibrium, F is equal to Fr and L will become L plus delta L. Fine. Now we have to find how much work is done to extend this length L by delta L. Now say let F is the applied force to the, say, wire of length L and due length L and the area A. Now due to the force, length of the wire is increased by delta L. Increased by delta. There is the length becomes L plus delta L. Now we know what do we know? We know that for longitudinal strain and longitudinal stress, the elastic constant is given by Young's modulus. Young's modulus, that is Y, is stress by strain. So here the stress is force per unit area and strain is simple, that is delta L by L. So F into L by A into delta L. So this is the strain. Now what we need? We need work done. So for work done, what we need? We need the force, which implies force is equal to YA delta L by L. Now let us consider that, say say this is the final increment in length, that is delta L. Now if we say that during this extension dl, the dl, the small extension is a line element, small extension, and to increase the length by dl, let the work done is dw. So let dw be the work done for increasing the length L of well by dl. Fine. Now by definition, the work done dw is equal to is f dot dl f dl cos 0 cos theta, since theta is equal to 0, as f and dl in same direction, force is along extend. So theta is 0, why? Because f and dl are in same direction, so force is along the extension, that's why. So it is equal to f dl, as cos theta is cos 0, cos 0 is 0, sorry, cos 0 is 1, sorry, cos 0 is 1. So the f is given by ya delta L by L dl. Another thing, say this delta L, we can write it as small l. This is delta L, so this delta L can be written as small l. Strain by stress, just replace this delta L by small l for easier calculation only. F L by A L, small l, because if this one is L, small change in L is dl. If we have taken delta L, then small change in delta L is d of delta L. So dw is given by yal dl by L. Therefore total work done to produce the extension of L is w is equal to dw if you take total work done, which is equal to 0 to yal dl. As y, a and l are constant, it will come out, that is l dl 0 to l. So here if we do integration, we will see that l dl is given by, say, integration of x to the power m dx is always given by x to the power m plus 1 by m plus 1. Fine, this is the formula. So here L to the power is 1, this will be L square by 2, that is L square by 2, 0 to L, that is the initial point, final point. So for initial and final point, how we put y by a L, For L square, final point is L, that's why L square by 2 minus, put this 0 values, 0 square by 2, it is 0. So W is equal to YA L square by twice L. Now, as you will see that this YAL by L, so YAL by L, there is a half there, fine. So YAL by L into L. So what is the elastic potential energy? The elastic potential energy is equal to the work done, which is equal to the half. This is the force, there is a tension, half into tension into extension. How this tension? Since tension is equal to force, which is equal to YA L by L, and L is the extension. Now, say for energy density, now for energy density, say here elastic potential energy is the work done. Work done is equal to, this is half into this term and this term, half, this term is extension, this term is the tension or force, because tension is force equal to this one, into smaller is the extension. Now for energy density is potential, is the potential energy by volume, that is work done by volume, is potential energy by volume. So here we will see that you can write like this also, half into tension into extension. So here half into tension into extension divided by volume. As we know, volume is area into length of the wire. This half into, this is F by A is stress, and L by L is longitudinal strain. It is longitudinal strain. Therefore, we can conclude that energy density is nothing but half of stress into strain. So now in this discussion, what we see, so we saw that during an extension of a wire or any longitudinal element, when we increase the length by using a force, then a resistive force, that is the restoring force, acts. So to maintain that wire or that rod in a deformed form, we have to work against the restoring force. So work done is defined, you will know that work done is defined by dot product of force and the length in which the force is applied. So work done is F dot dl. Now to increase the initial length was L and it was increased by a length small l. Now if you consider that dl be a small extension, then the work done was given by dw equal to F dot dl. So as F and dl are same direction, so dw is F into dl, and we have found this expression. Now for total work done, what do we need? We need to integrate it. So in this relation, the variable is only L. So the work is to be done to increase the length of the wire by, say, from L to L plus L. That is L plus 0 to L, 0 to L. Now by performing this integration, what we got? We got this expression. W is equal to half into YA small l by capital L into L. So this one is force. So elastic potential energy half into tension or force into extension. And energy density, by definition, it is the energy density. It is potential energy by volume. So by putting the volume V as A into L, we get a simple formula of energy density, that is half into stress into strain. Now we will move to another strain which is also important. It's called shearing strain. So now let's come to shearing strain. So for shearing strain, as you can see, you can remember from our previous class, that what is shearing strain. Suppose this is a cube where the lower surface AB is fixed. Now if we apply a tangential force, here the force should be tangential. Now if we apply a tangential force F in this face DC, what will happen? As it is fixed, the face DC will move along the direction of the force, say by a distance x. So as a result, the perpendicular direction AD is turned by an angle theta. So that theta was the shearing strain produced in the body. So as we have also learned that shearing strain is also given by x by L. Fine. So now the force is tangential and this AB plane is fixed and the force F is applied on the DC plane, and as a result of this, the DC plane moves to D dash C dash, and as a result it is displaced by a amount x in the direction of the force. So now let us find the work done in displacing the DC to D dash C dash. So the work done is, so if we consider that initially the work done in displacing a small amount dx be dw, so work done in displacing DC by amount say dx along DC using a tangential force F. What is F? F is also along force F along DC. So it is given by say dw. If the force and displacement are in same direction, so dw is F dot dl, which is equal to F dl, as F and dl in same direction. Now what you can see, we'll write the value of force. So for shearing strain, this is very important. For shearing strain, the modular force of rigidity is given by F by A is the stress divided by strain. Now another thing, you must know that A is the area of the surface and theta is the strain. Here A is the area of the tangential surface and theta is shearing strain. What is A? As we have discussed, so this is the this is the force, then this is the area, this is the tangential area, not this one, this is theta. So the force is now given by eta A theta, therefore dW is equal to eta A theta dl. Now as you can see, A can be written as L square. Since A can be written as L square, it is S cube, that's why A equal to L square. And theta by definition is x by L. Tan theta equal to x by L. So for small theta, is theta equal to x by L. So this dW can be written as L square x by L dl dW. So this square and L will cut, eta L x dl. Sorry, you will know. Okay, see, this is x, this is x, so a small displacement will be dx, so work done will be dx, so will be dx. So replace dl by dx, so it's fine. Therefore total work done to produce a linear displacement of x is work done equal to 0 to w, that is 0 to x. So in the similar way, eta and L are constant, x dx, x square by 2. So it is x square by 2, therefore work done is equal to eta half of eta L x square. Now as you will see, so as you will see, W is equal to half of eta L into x square. So we must get a force expression from here. To get a force expression, we know that force is NA theta, or you can say force equal to NA theta is x by L. Fine. This, you keep this in the back of your mind. You need to use the keep it in the back of your mind. So we must write it as half eta. Now here we can write it as L square by L, that is L. Then we can write it as x square. L square is A, that is A by L. So this one you can write as NA x by L into x. So W is equal to half into NA x by L into x. This is NA x by L is force, is equal to half into force into extension, There is half into force, and force is eta A x by L. Fine. So now the elastic, so the potential energy is equal to work done, which is equal to half into force, that is tangential force, into the extension. Fine. Now energy density, this is the tangential force, and this is extension in tangential direction. So energy density, is defined as potential energy by volume, which is given by half F into extension, that is divided by volume. As you can see, this is half into force into extension divided by volume. So volume you can write as A into L, so that is half into force to X. So force by area is stress, that is half into F by A by X by L, equal to half into stress into strain, which is equal to energy density. So similarly, for tangential, for the longitudinal strain also, the energy density was given by half into stress into strain, and for the case of shearing strain also, the energy density is given by half into strain into stress into strain, while the potential energy is given by half into force into extension. So there the extension was in tangential, in longitudinal region for longitudinal strain. Here the extension was in the tangential direction, as the force was in tangential direction. So these two relations are very important. So I think that is enough for today. So if you have any queries, please write to me.